All right, we're going to finish up this chapter by looking at periodic trends. As we go across a periodic table or down the periodic table, what happens to various properties of our atoms. So the first thing we're going to look at is atomic radius, the size of the atom, the radius of the atom. And what we find is as we go down the periodic table, down a group, that the atoms get larger. Now that's to be expected because we go from n equals 1 to n equals 2, n equals 3, the principal quantum shell. And we know the principal quantum shell tells us about atomic size. So we would expect a potassium to be larger than a sodium because potassium is under sodium in the periodic table. As we go down the table, the atoms get larger, putting more electrons into orbitals that are further away from the nucleus. What might not be expected, though, is as we go from left to right across the periodic table, the atoms actually get smaller. Now, why is this? We keep adding electrons. Why is an atom going to get smaller if we're putting more electrons into the orbitals? The answer is this. Let's look at the lithium atom here. Lithium has 3 electrons and a 3+ charge in the nucleus. It has 3 protons. So here's our 3+ charge in the nucleus. Recall that the first 2 electrons in lithium, the first 2 of the 3 electrons, are in the 1s orbital. And so here are these 2 electrons in the 1s orbital. The next electron goes in the 2s orbital. Turns out these 1s electrons do a pretty good job of shielding this 2s electron from the 3+ charge. So if I have 3+ in the nucleus and 2 negative charged electrons shielding that 3+ charge, this 1 electron here really only feels a net +1 charge. It's trying to feel all 3 positive charges from the nucleus, but it can't because 2 negative charges are blocking 2 of the positive charges from the nucleus, letting this guy only feel 1 positive charge. But now let's go to the next element over, beryllium. It is directly to the right of lithium. And beryllium has 4 protons in the nucleus, 4 electrons in a neutral beryllium atom. But look what happens. We have our 4 protons in the nucleus. We still have the 2 electrons in the 1s orbital, effectively shielding 2 positive charges away from these 2 valence 2s electrons. However, here are 2 valence 2s electrons. This electron up here is not doing a very good job of shielding a positive charge from this electron here. They're in the same 2s orbital, in the same quantum shell, n equals 2. So we've added a positive charge, a full positive charge to the nucleus, but our extra electron that we added is not adding a full negative shielding to that nucleus, which means this electron feels greater than 1 positive charge. It feels there was 4 positive charge here, 2 electrons block 2 of the positive charge. This electron only blocks a little bit of that extra positive charge. Therefore, this guy here feels around a 1.6 positive charge, around 1 to 1.7 positive charge. Which means this last electron that was put in feels more positive charge than the last electron that was put in for lithium. Which means this electron is held tighter. The more positive charge attracting more negative charge means Coulomb's law tells us the force of attraction is going to be stronger. This electron is held tighter, which means the atom is smaller. This electron is being held closer to the nucleus due to the force of attraction between this negative charged electron here and the greater than 1 positive charge. So that's what happens as we go across a table. Elements get smaller and smaller. So if we look at our periodic table, and for instance we say, okay, what do you expect the size of a sodium to be compared to the size of a chlorine? Since these are in the same row, we'd expect a chlorine to be smaller than the sodium. And in fact, the chlorine is smaller than the sodium, because as we go from left to right, atoms get smaller. All right. But now let's look at the ionic radius. What happens when we take our neutral atom and make it an ion? Well, let's see. It turns out cations are going to get smaller than their original atom. Anions are going to get larger than the original atom. For example, let's look at Na plus versus F minus, and we'll start by just looking at a neutral sodium compared to a neutral fluorine. All right. Looking at the periodic table, here is sodium in N equals 3. The last electron is in a 3s orbital. Here's fluorine. The last electron is in a 2p orbital. Okay, well, we know if we go down the periodic table that sodium will be larger than lithium. We know as we go across, things get smaller, elements get smaller. Therefore, we know fluorine is smaller than lithium, which tells us right away that we expect this sodium atom to be a bit bigger than this fluorine atom. Because as we go down the table, atoms get larger. Going from right to left, atoms get larger. So we expect the sodium atom to be larger than the fluorine atom. And it turns out we are correct. It's quite a bit larger. The sodium atom is 186 picometers in terms of atomic radius. The fluorine is only 72 picometers. So a sodium atom is more than twice the size of a fluorine atom. If we look at the electron configuration for sodium, we see it as 1s2, 2s2, 2p6, 3s2. Oops, oh, no. Sodium, 3s1. Yeah. All right. We're in the N equals 3 shell with that 3s1 electron. For fluorine, 1s2, 2s2, 2p5. We're only in the N equals 2 shell. But look what happens when we take away that electron. What happens when we take away this 3s1 electron? Well, we're left with sodium is 1s2, 2s2, 2p6. The same electron configuration as neon. So Na plus is isoelectronic with neon. But let's look at the fluoride. If we add an electron to fluorine to make F minus, the electron configuration now is 1s2, 2s2, 2p6 also. So now the sodium cation and the fluoride anion have the same electron configuration. Both of them are isoelectronic and isoelectronic with neon. But there's a difference. The sodium has 11 protons in the nucleus. And when we look at the number of electrons, 6, 7, 8, 9, 10, the sodium cation has 11 protons in the nucleus, 10 electrons floating around. The fluoride anion only has 9 protons in the nucleus because the atomic number of fluorine is 9, but it also has 10 electrons. So the question is, what's going to hold on to the electrons tighter? 11 plus charge in the nucleus holding on to 10 electrons, or 9 plus holding on to 10 electrons? Well, we can see that the larger the charge of the nucleus means these 11 protons are going to hold on to these 10 electrons tighter than 9 protons can hold on to 10 electrons. And we see that. The sodium plus cation is 95 picometers. Note, it went from 186 to 95. The sodium cation is about half the size of the sodium atom. The fluoride, this fluorine atom had 9 protons and 9 electrons. Now it has another electron. It can't hold on. These 9 protons cannot hold on to that extra electron nearly as well. So the anion gets larger. The fluoride anion is 136 picometers compared to 72. So note, the sodium atom, when it became the sodium cation, its size was about halved. When the fluorine atom became the fluorine anion, its size nearly doubled. Now, what would we expect for O2 minus compared to F minus? Well, looking at our periodic table, Here's oxygen, here's fluorine. Whereas we know fluorine's a little bit smaller than oxygen is, we expect that. Note, with fluoride, we add 1 electron, 9 protons, attracting 10 electrons. With oxygen, O2-, we've add 2 electrons, 8 protons, attracting 10 electrons. Wow, 8 protons attracting 10 electrons versus 9 protons attracting 10 electrons. 8 protons cannot hold on to their electrons as well as 9 protons can. So we expect an O2- ion to be larger than the F- ion. And that is what we see. All right. The last thing we're going to look at for this chapter is ionization energy. Now, ionization energy is the energy it takes to take your neutral atom, technically in the gas phase, add enough energy to it so that it becomes a cation. We remove an electron from your neutral element. And if we have a neutral element and we remove 1 electron to make it the positive element in the gas phase, we call that the first ionization energy. If we start with the positive ion in the gas phase, add more energy to remove that second electron to make it a 2+ ion, we call that the second ionization energy. And what we see as we go across the periodic table, ionization energy increases. As we go down the periodic table, ionization energy decreases. And this should be completely expected, because the smaller an atom is, that means the more tightly it is holding on to its electrons. The more tightly it's holding on to electrons, the more difficult it is to remove an electron. Since size decreases, atoms get smaller as we go from left to right across the periodic table. You would expect the smaller atoms to hold on to electrons more tightly. You would expect ionization energy to increase, take more energy to remove that electron as we go from left to right. And that is what we see. By the same token, since we know that atoms get larger going down the periodic table, the larger the atom, the less tightly it's holding on to its valence electrons, which means the easier it is to take those electrons. Ionization energy decreases. It becomes easier to take electrons away from larger atoms as we go down the table. Note, there are a few exceptions to this rule, but with what we've already learned, we can see why, yeah, you'd kind of expect some of these exceptions. For example, nitrogen versus oxygen. When we look at the periodic table, we see that nitrogen is a little bit larger than oxygen. Note, we're going from left to right. Atomic size gets smaller. Oxygen's a little bit smaller. We would expect it to have a higher ionization energy because it's a little bit smaller. But in fact, oxygen has a slightly lower ionization energy. It's a little easier to remove an electron from a neutral oxygen compared to a neutral nitrogen. Why is that? Well, let's look at nitrogen's electron configuration. In the valence shell, we have 2s2, 2p3. Recall Hund's rule. We're going to put those 3 electrons to maximize their spin multiplicity, is what we call it, to have the maximum number of parallel spins, and that gives us a half-filled subshell, which we know is stable, is lower in energy. Oxygen has 1 more electron, so that extra electron has to get paired up with one of these electrons. Notice we're no longer in a half-filled subshell. We've got 1 more electron in there. Note that it is actually paired with another electron in there, and 2 negative charges really don't care to be in the same orbital if they don't have to be sharing the same space. They repel each other. So it turns out that it's easier to remove this electron because we get rid of the repulsion with the other electron, and if you remove this electron, you go back to it'll be isoelectronic with nitrogen, which has a half-filled stable subshell. That is it for this chapter. Note the book also talks about electron affinities. We will not go into electron affinities at this time.